Hello and welcome to these video notes on 12.1 Trigonometric Identities. So to begin, let's start with some definitions. So a trigonometric identity, it's an equation involving trigonometric functions that are true for all values for which every expression in the equation is defined. A lot of words, we're going to talk about it later. A Pythagorean identity, it's an identity that expresses the Pythagorean theorem, so a squared plus b squared equals c squared, in terms of trigonometric functions. So what we're going to do first is we're going to go over our reciprocal and quotient identities from our previous unit. So here we go. Sine of theta is 1 over cosecant of theta, and cosecant is 1 over sine of theta. Cosine of theta goes with secant, so it's 1 over secant of theta. And so secant of theta is the same thing as 1 over cosine of theta. They're reciprocals of each other. And then tangent and cotangent are reciprocals, so we get 1 over cotangent and 1 over tangent. Okay, so those are our reciprocal identities. Our quotient identities is tangent of theta is y over x, so it's sine of theta over cosine of theta. And since cotangent is the reciprocal of tangent, we do the reciprocal, so it's cosine over sine. Okay, so you will need to remember these because we're going to be using them to verify identities, which is what we're doing today. So before we do that, we need to understand what a Pythagorean identity is. Let's first look at our Pythagorean identity, or our Pythagorean theorem using the unit circle. So usually it would be a squared plus b squared equals c squared. Well, our a squared is x, b squared is y, and c squared, which is 1, because we're working with the unit circle, well, 1 squared is 1. So that's how we get that x squared plus y squared equals 1. Well, again, since we're using the unit circle, we learned that it was cosine comma sine. So using that same idea, if x is cosine of theta and y is sine of theta, then we can use that by substitution and say cosine theta squared plus sine theta squared equals 1. Now, when we square something, we can also rewrite it as, I'm going to change the order as well, sine squared theta plus cosine squared theta equals 1. And so you cannot write sine squared theta as sine theta squared unless you have parentheses around it. Okay, so what we have is sine squared theta plus cosine squared theta equals 1. Now, if we use subtraction, we can move pieces over. So we could subtract sine, and we could then subtract cosine to get a different version of this Pythagorean theorem. And so we can get cosine squared theta equals 1 minus sine squared theta. Then, if we do the other one, we can get sine squared theta equals 1 minus cosine squared theta. Now, unlike above where we change the order, we can't change these orders because the sign of the trig value does matter. Okay. So let's go to the next page, because what we're going to do now is we're actually going to find the other two Pythagorean identities, or Pythagorean, for trig. So where this comes from is we're going to divide the function all by the same. So for this first one, we're going to divide everything by sine squared theta. The reason this is okay is because we're doing it to everything, so it's keeping the equation balanced. So what we get, well, anything divided by itself is 1 plus cosine squared theta over sine squared theta equals 1 over sine squared theta. Well, using everything we saw on the previous page, cosine over sine is cotangent, so this is cotangent squared theta, And then 1 over sine goes with cosecant, so this is cosecant squared theta. And that is our other Pythagorean identity. Okay, so we divided everything by sine. Let's now take the same exact Pythagorean theorem, our identity, and instead divide by cosine squared theta. Okay, and so we get sine squared theta over cosine squared theta plus 1 equals 1 over cosine squared theta. While using the same rules, again, we used for the previous problem and on the other page, sine over cosine goes with tangent, so we get tangent squared theta plus 1 equals 1 over cosine goes with secant, so we get secant squared theta, and that's our other Pythagorean identity. And so we have 3 Pythagorean identities, and so that's what we're going to write down here. So we get sine squared theta plus cosine squared theta equals 1. 1 plus cotangent squared theta equals cosecant squared theta. And then finally, tangent squared theta plus 1 equals secant squared theta. Now, we did this on the other page, but we're now just going to have it all together. We can move these over to the other side to find out different pieces of information. And so we can get sine squared theta equals 1 minus cosine squared theta, and cosine squared theta equals 1 minus sine squared theta. On the next one, we can subtract 1, so we can get cotangent squared theta equals cosecant squared theta minus 1, and then 1 equals cosecant squared theta minus cotangent squared theta. And our last one, we can get tangent squared theta equals secant squared theta minus 1, and then 1 equals secant squared theta minus tangent squared theta. And so those are all of our Pythagorean identities that we can have. The whole reason we need to do this is we are going to be simplifying a trigonometric expression. Now, there's a bunch of ways that you can do it. You can choose to just change the expression into sines and cosines. You can look for formulas to substitute in. If you have fractions, find a common denominator. You can use algebraic manipulations like factoring and distribution. And then sometimes you're going to have to just restart the whole problem, and that's why we use pencil so much in math. So this is what we do. Here we go. We can rewrite tangent of x using cosines and sines. It's sine of x over cosine of x. And so using that idea, the cosines cancel, leaving us with sine of x. And there you go. Okay, so secant goes with cosine, so it's 1 over cosine of x. And cotangent is cosine of x over sine of x. And so again, the cosines cross cancel, but we're left with 1 over sine x, which is cosecant x. And then our last one, there's a couple ways we can think of it. Let's say I gave you x over x squared. Well, since they're the same base, we would subtract. And since there's more on the bottom, our base would stay on the bottom. Likewise, we have cosine x over cosine squared x. We have 1 on top and 1 on the bottom, so we would get 1 over cosine of x, which is secant x. And so that is how to simplify a trigonometric expression. Now what we're going to do is we're going to use complex fractions, so we're on to the next page. So we can have 3/5 divided by 1/2. Well, we keep, change, flip, and so nothing cross cancels, so we just multiply across and we get 6/5. We already did this problem, so you can just cross it out. For our next one, we would get 10 divided by 5/3. Well, keep, I'm going to turn it into a fraction, change, and then flip. On this problem, we can cross cancel. They both have 5 in common, and then we multiply across to get 6 over 1, which is just 6. So using that same concept, we can actually change this fraction into something else. Well, 1 minus cosine squared x is sine, oopsies, let's make it look like not an 8, sine squared x. That's using our Pythagorean identity. And tangent squared x is sine squared x over cosine squared x. So very similar to the problem above, we have dividing two pieces. So we're going to keep, change, and then flip. And so what happens here is our sine squareds cancel out, leaving us with just cosine squared x. Okay. Now, so that's when a fraction is being divided by another fraction. Let's say we are adding two fractions with one term on the bottom. When this happens, you can separate that numerator, and so we would get 1 plus b over a. And so let's look at this problem. Again, we have one term on the bottom, so we can write it as tangent of x over tangent of x plus cotangent x over tangent of x. And we get 1 plus, I'm going to do some scratch work for this over here. So we have cotangent of x divided by tangent of x. Well, we can rewrite tangent of x as 1 over cotangent of x. However, we can't cross cancel because we're dividing. We have to keep, change, flip. And so when we multiply, we get cotangent squared of x. And so this is a Pythagorean identity, which gives us 1 plus, right? Ooh, yeah. This is cosecant squared x. There's our final answer. Okay, now let's look at our next one. This one, to add fractions, we have to have the same denominator. So we would multiply the top and bottom by 4 and the other one by 3. So that would give us 8/12 plus 3/12, which we can now combine to make 11/12. Well, we can do that same thing on this type of problem. We can multiply by the other denominator, so we can combine them. Minus sine x, 1 minus sine x. And so, if we distribute 1 in, we would get 1 plus sine x all over, I'm going to pause for a moment, plus, again, distributing that 1 in, 1 minus sine of x all over, let's see, you should have some space right here. Let's do box method because we're multiplying those two expressions together. So we have 1 plus sine of x times 1 minus sine of x. Now what happens is you should start to see something interesting happen. Sine squared x. Our middle terms cancel out, and so we get 1 minus sine squared x. This is dots. It's a difference of 2 squares. It's coming from the original part. And so we are going to have, since now they have the same denominator, 1 plus sine x plus 1 minus sine x all over 1 minus sine squared x. So there's a couple things we can do. We can combine like terms. So 1 plus 1 and sine of x minus sine of x. And we can also turn that bottom into a Pythagorean identity, which will give us 2 over cosine squared x. Well, 1 over cosine squared x is secant, so we get 2 secant squared x. Okay. We got a example 4 together, and then I'm going to have you do some problems on the next page. Here we go. So, factoring a GCF, these both have a squared in common. So we can factor out, sorry, 1 minus b. And that would be it. Okay, so likewise, in the problem below, they both have cosecant squared x in common. And we're left with 1 minus cosine squared x. Well, cosine squared x is sine squared x. And while I'm doing it, cosecant is the same thing as 1 over sine squared x. And so the sides cancel out, and we're left with 1. Not 0, but 1, because when we cancel things out, what they're really doing is going to 1. Okay, now what we can do with the next problem is we can do our big X. What two numbers multiply to get 1 and add to get -2? -1 and -1, so we get a minus 1 squared. Well, we can do the same thing. Notice how it is a quadratic. And so what I like to do is I like to say, okay, x equals sine of x. So that way I'm kind of replacing it for a moment and I'm going back to my root. So I would get x squared minus 2x plus 1. Well, we can now do our big X, which it should look familiar. What two numbers multiply to get 1 and add to get -2? -1 and -1. And so we would get x minus 1. Well, we can now bring back in substitution. I forgot the squared. And we can substitute back in sine x for x minus 1 squared. And there is your answer. And we actually can't write that as cosine squared x because it's not, we can't distribute that squared in. That's a no-go. So that is as far as we can go. Okay, so on the next page are some examples. I want you to do A and B and D. If you want, try C. Let's do C. A, B, C, and D, the first 4 problems. Okay? Try those on your own, and we will go over them and the rest in class together, and come with your questions.